Some people ask me to do it in English. It's okay for everyone? Okay, cool. If I speak English too quick and maybe too fast, because sometimes it happens to me, just okay, and I will slow down. There is no problem for this. So, hi everybody. I'm very happy to be there to speak with you about containerization and virtualization. And for those who don't know me, my name is Quentin Adam. Oh, sorry. My name is Quentin Adam. I have a very unpronounceable Twitter handle, and you can find me everywhere on the web with that. And my day-to-day job is leading a company called CleverCloud. CleverCloud is an IT automation company, so basically what we do is keep your application online. So if you have an application, you just git push, and we successfully deploy it in servers, and there is auto-healing system, auto-monitoring. We manage the security update for you. There is an auto-scalability thing, you know, this kind of stuff. So basically, you just write some code, push it, no more problems. And we have awesome stickers and awesome t-shirts. So, what's fun about this company is we have customers in 1,500 cities in the world. Big companies, boring companies like banks, insurance companies, things like that, small startups, people in Kathmandu, people in France. So we discover a lot of things about how people work, and for this, we have a lot of life, you know, supporting these guys. We learn a lot about good design, bad design of application, and we try to give back to the community with talks and try to improve the way everybody is writing code. So that's what we do. Okay, so why we will be speaking about virtualization, container, and all this kind of technology. Just to be sure, who in the room have ever managed a Xen cluster, you know, Xen virtualization cluster? Using Amazon Web Service, Heroku, CleverCloud, more, cool. DigitalOcean, Docker, Rocket, EdXC. Okay, cool. So at the beginning, everybody was using very big computers. You know, this room, big computer with a lot of things and very small capacities. So at the beginning, computer was very big, but can only run small piece of code. And there was only one software, and there was no, you know, there was no multiple software in the same computer. It was only, you know, calculation of one software. And then we happening to have more and more powerful computers, so we start to have multiple software running on the single hardware. So at the beginning, you have only one software, and then multiple software written by different people running on the single hardware. And what's happening is it's lead to something, oh, awkward. It's lead to something what's a multi-process system inside the operating system. And the multi-process inside the operating system lead to something which is the process scheduling. You know, upstart, initd, systemd. I'm pretty sure you remember the old story about systemd, things like that, a few years ago. And all this kind of stuff is about how we process, schedule all the thing. And it's lead to something inside Unix, which is pretty important with its PID1. PID1 job is to manage a process. And this is very important to understand. PID1 have many things to do. So then we lead to the spaghetti ops management. Remember early 20s, like something like 10 years ago, when people have multiple software inside only one operating system with, you know, Apache, the MySQL, one Java application, I don't know what with Perl, you know, this kind of all the thing inside the same servers, and it was leading a lot of problems. Then we start to unlink the hardware capacity from the software management, saying, okay, we have something able to calculate things, but we need to unlink them. So have the power of calculation and computation on one part, and the software management on another part. And for this, we have invented the process. Process is something able to be one software running on something. There is a PID1 managing the process. Everybody is happy. There is process. But the problem with process is the isolation. Isolation is a multiple concept system. So you need to understand that the isolation is based on the software dependencies. You know, when you're using a software, like for example, you have a website managing videos. The software needs to have FFmpeg running on the system. So you have a dependencies to FFmpeg. So inside the OS, you have a dependencies to FFmpeg, and you need to manage these dependencies. The isolation is also about the security. If a process can write inside another process, you have a big problem. And the other thing is the hardware resource access. If one process can hit the whole hardware capacity of the virtual machine, you have a problem. So basically, these three parts of the pillar of what is isolation. So people start thinking about how to manage the problem of isolation. And then we invent root. Root is something we call change root. What is the basic idea? Is a Unix philosophy. Everything is a file. If you are able to say the root file system is no more this, but it's this, you change the way the whole operating system works because everything is a file. Okay? Everybody get it? It has been invented inside Unix in the late 17th, early 18th, and it was been here around, and it was introduced inside Linux in the late 19th, maybe 2001. I think it's 2001 inside Linux, and it's work on the file system. So basically, how it works. Everybody can read there? There is no problem? Okay. Cool. I am in a pure Linux system, and I have several processes running there, okay? I decide to have a Node.js application. And this Node.js application is right to be sure we have a security issue inside it. In fact, if I write something in the header inside that, I will execute a command inside the system. So if I'm doing this, what we can say is date have been evaluated inside the system. So I have write a command. This is a security issue, but we assume we have done this on testing purpose. So basically, if I'm doing something like creating a file inside the temp directory, the problem is, inside the temp directory, there is a file. So basically, I can rewrite the binary of anything else inside the system, and it can be very frightening. So how I can isolate this to the whole system to be sure there is no problem? There enters root. Root is able to say, okay, inside a path, I have created the whole system, you know. There is the point where we know we are in root. We are cut there. That is the way everybody are looking at me like I am a crazy guy. So, and you can see there is a root level system, and there is the root level system, okay? If I decide to go on the root system, for rooting, you need to bind some of the file to be able to access, you know, device and proc and all the things. So, like I am a lazy boy, I will doing it quite quickly using copy-paste bullshit. Oh yeah, sure. So I'm root, I'm muting all the things. So basically there, what I can do is say, okay, I will root inside the new system. And when I am doing this, Okay, I am inside the root. Okay? If I am doing this, not for bash, which is pretty dangerous, but only for the server I want to execute, I can say, okay, I am shooting something there and making a node and I'm launching server 1. And the server is now running. So my system is still on root, but if we're doing a file system, a process listing, we can see there is the rooted operation. And with that, we can try to curl exec inside the system and create touch there. It's not working because there is no temp. There is no time directory. If I try to touch a file and I'm doing it like this, it will not be on the root file system. It will be inside this rooted file system. So kind of luckily I've managed a thing. The problem if root is not so secure. Example, I'm rooting myself inside the system and I have a script able to unroot to root again inside the slash. Okay. Make this, I unjailing, and I am the root file system. The other problem, like I am rewriting the whole system file, if I am rewriting the user, the shadow and password file, I will be able to log myself inside the root file system as a user who doesn't exist and become maybe a more privileged users. And this can be very nasty, And so to manage this kind of stuff, binary like su and sudo have managed to have compatibility issue there. You can sit down there if you want. There is some space there. And they manage to have this kind of no issue, but still there is a problem of containerization inside and isolation inside the root system. So it's have a very weird relationship with root. It's easy to break out, and there is a privilege escalation you can achieve using nasty binary system. But okay, you can manually manage inside a rooting system dependencies of software, and there is absolutely no hardware resource management. So we keep looking for another isolation system. People are talking about jails and containers. Okay, jails and containers are basically something like the whole OpenVZ, Linux vServer, LXC, Docker, runc, Rocket, everything. Okay, it's all the things, and it basically something very important you need to understand. The runtime, Docker, Rocket, LXC, doesn't matter. It's just a sugar pump around Linux syscall. Basically, the runtime is a Linux kernel. So when people say to me, Docker is able to manage this because it's written in Go, a low-level language, which is basically not true, but not the problem, it's not interesting because Go has nothing to do. The runtime is only Linux. It's only passing some calls to the Linux kernel. The thing is, all the jail and containerization system is based on the Linux namespacing. Linux namespacing is the ability, it's a feature introduced for root at the first, introduced in the Linux kernel in 2002, and extensively managed in 2013 to be able to map name of resource inside the system. You can have a namespacing of mounting, which is basically what we use when we are rooting something, But also on PID, the network interface, the hardware calls, interrupting hardware calls, the old host name system, which is ATS, and the users, to be able to remap PID of users, user ID. And this is just, a map with, if you have one, you are considering like 3. It's only this. Namespacing is not a security feature. It's only a mapping feature saying, okay, in this world, Bob will be called Kevin. And that's all. And it's basically what's done namespace. The old features people are using when they are doing some container stuff is the Linux C groups. Linux C groups have been introduced in the kernel in 2008, and there will be a V2 ready quite soon inside the kernel. And Linux C groups is something made to only be able to make some quota and limitation on the hardware allocation inside the Linux system. So if you're taking the namespacing plus C groups, you have something where able to manage the hardware access on some process inside the system. Downside is Linux C groups are not precise. You cannot really rely on it. Okay, it's not bulletproof on managing really resources. So what you need to understand about containers is there is no box, there is no high run, there is no light VM. It's only a Linux process with a bunch of special permissions. Okay, if I am doing a simple, I am connecting to a Docker machine system. In this Docker machine, I have some containers running. These containers are basically a Titan graph database, a Cassandra graph database, an Elasticsearch database. And if you are looking on the whole process running there, okay. You can find all your process. Basically, what's running inside the containers is just running on the system. For example, this is your Cassandra running inside root on top of your host. Okay? There is no jail, there is no containers. It's only picture to just see in your minds, but it's only processed on the system. And what it's called on this is, okay, we are running inside a process. And it's called the ability to access to the process. Okay? The problem with process is the isolation and side effect. There is many things running inside an operating system. If you are in some container place, okay, and you say, okay, I have hundreds of running containers inside my host. These containers are only process. I will start 20 RIAC database inside my host. RIAC database is awesome database, but it needs something, a lot of file open in the same time. Each file open is something we call a file descriptor. Just think about that. If I'm using a lot of file open, the number of file open in the system is not wisely chosen by each container. It's a global counter. Okay, all your RIAC have eaten the whole capacity of the system of opening a file. You have a simple PHP application running some logs, and it's switching the log rotation state. It wants to open a file. It can't, because there is no more file descriptor available. But the monitoring say to you, everybody is working fine, but the whole system is going down because you cannot open any file. This is the kind of side effect you can have on this kind of stuff. Just made an example. This is just a fog bomb. What is the name exact of the command I have made for this? I do not remember. Just 1 minute. Okay, this is just a fork bomb. Not interesting thing, just a fork bomb. If I'm launching this fork bomb, everybody is happy, okay? We're running the fork bomb. No. I say, okay, how many processes there is there? There is 15,000. How many processes have been there? Okay, there is more and more process. It's cool. It's cool. There is more and more process. And at one time, all these processes are going up because it's all inside a container, and there we have a problem. We cannot create more process. And I have been down from the system. The old system monitoring say to me, everything is okay, but I cannot create any process more just because one container I've made some bullshit. Just remember this. The isolation is not totally, because there is a lot of system-wide available feature and metrics, and all the containers will refer at the same thing because it's only one kernel. So this is going down. So this is a problem with isolation. You cannot really isolate things because all the system-wide possibility of fails, you know, like there is a file descriptor one, but there is many more ways to have problem inside of a system. And it's the same, exactly the same problem for all the containerization system, because the old containerization system are relying on exactly the same runtime, which is the Linux kernel. The other problem is about the Linux philosophy. If you're starting a container, and the container have to start more process, you are doing the job of a PID1 inside the PID1. What is the PID1 job? PID1 has many more jobs. And one of the job important of PID1 is killing zombie process. So basically, if you're using a system creating and deleting a lot of process in the same time, you will have a problem. Nobody is making the job of cleaning up after you. And you cannot launch two systemd process inside one Linux system. So you have a big problem there because you will have a lot of zombie process. The other problem is if you are just asking for a daemon to start a process, basically Docker is not, when you start a process with Docker, you just have the Docker client saying to the Docker daemon, okay, I want to start a process. And the Docker daemon start the process, which is basically the job of PID1. So basically, the Docker daemon is managing process like PID1, but it's not PID1, and it's fighting together. You can write on the internet a lot of things about that between the systemd and the Docker team fighting together because there is a problem. Docker want to be the PID1, but don't want to be the PID1 responsibility, you know. And there is one of the problems of the Linux philosophy inside this. The other problem is if you're taking the old binary of the system, Linux libraries, glibc, everything, which is the base of the container, and putting this on inside another operating system, the only binary you don't get is the kernel. And the kernel and the glibc incompatibility testing system will be very weird. Because it's important, you know, to have the same kernel at the same time. So basically, when you say it's all based on the same thing, you can have a problem. The other problem is about the monitoring. Monitoring needs to be a process able to access on many things inside the system to get some metrics. So you cannot have proper monitoring inside the container. You need to be outside and be system-wide monitoring. it's not the same job that what we do today with simple monitoring system. You need to have a complex monitoring system with ability to, reload its configuration each time you change a container way. So this is the main problem processing and jailing and containerization was managing 10 years ago when there was putting in the stage. And the problem is made like it's changing a lot of the system behavior. And you need to adapt a lot of the code of the system and the access of the system to be able to perform a proper isolation and a proper access on many things. It's understandable what I am saying or not? Okay? So, the search is not over. How to take some containerization system. There is a guy in France who have invented QEMU. QEMU is something we call emulation. Basically, there is a software thinking is a CPU and managing to be able to replace your CPU. When you're using Dolphin GameCube emulator, for example, it's exactly what's happening. There is a Dolphin CPU emulated in top of your CPU, and as your CPU is so fast, you are able to just create a whole virtual CPU and running an operating system on top of it. QEMU was great to managing this kind of tests because we can manage a lot of tests, but it was really slow. Then people start trying to do the thing like, okay, if we're starting a small kernel, we will call it Xen, and patch the kernel Linux to speak with the Xen system. And we start the kernel Linux like a process for Xen. And then the kernel Linux will manage, the patched kernel Linux will manage its whole OS. It will work. It's called Xen. It's paravirtualized. Paravirtualization is a weird name because basically everybody have used this term for different occurrences. Basically, it's not a good term, but Xen are managing this, and it's basically what's running on top of Amazon Web Service. Then Intel come in the game. In 2003, Intel are creating something called VTX, virtualization instruction inside the CPU. What is VTX? VTX is the ability to run two software without they notice the presence of others. It's a context switching system inside the CPU, able to say, if one OS run and I context switch to another OS, the two OS don't know they're running each other. Okay? They absolutely don't know there is another operating system running inside the same CPU. And this virtualization instruction is very interesting because it defines how to access to the hardware. At the beginning, the Intel guys were thinking, okay, we will be able to run Linux, Windows, and FreeBSD inside the same CPU, and we will rack 3 different network cards, and each network card will be accessing only by one operating system. So it's not interesting, to have one CPU, RAM, and 20 network cards inside the same hardware. So basically what people do is the first OS gets the IP and then have some networking, like there is a router or the switch virtualized inside the first operating system. It's okay for everyone, the networking part, or do you want I re-say it in French? C'est bon pour tout le monde? What is interesting with this is it's a plain old operating system. You don't need to edit it. You just need to have a small piece of software saying, okay, I'm the first operating system, I'm the second operating system, and managing who is responsible for the CPU at this time. But there is absolutely hardware separation and isolation between the operating system. So basically, from the virtual machine perspective, the software dependencies is total, the security is total with the guarantee of hardware, and the hardware resource control is really easy to access because it's encoded inside the Intel virtualization instruction. Basically, Um, okay, sorry, I have to activate the Wi-Fi. Okay, I'm not sure it will work, but if we connect to a test server of Clever Cloud and we're running a process list of the server, when there is a virtual machine running there, you cannot see the process running inside because the virtual machine don't know is a virtual machine. You know, there is no process system. The CPU is totally and absolutely isolated from one to the others. And you can run it like this, a lot of virtual machine. For example, if I grab on there is like 134 virtual machine running on top. It's not a problem, you know. It will run. There is no problem of running a lot of virtual machine inside a simple system. It's just context switching for the processor. Okay? So, what people are concerned about virtual machine? Performances. People say to me, virtual machines are slow. First, it's not true. Who think Python is more fast than Java? Lot of people think that, because when you're writing a command line on Python, Python starts very fast, you know. But Python is slow compared to the JVM. But the JVM is slow to start. And people think there is a link, but it's not true. Java is fast, Python is not. But you feel like it's fast. And you know, it's not the same thing. And this is the way you need to understand performances. A lot of people think virtual machines are slow because when they're using it in with the display inside their computer, it's slow. Why it's slow? Because when you're using the display system, you need to access the screen, which is an emulated screen with an emulated graphic card and everything like that, and this is slow. But the processor, you know, and the CPU level is very quick. So first, this is why. And second is you can start a virtual machine really fast. At Clever Cloud, when we ask for the orchestrator a new virtual machine, and the virtual machine say, okay, we start to deploying the application of a customer, there is only 6 seconds. So it's not slow. It's because a lot of people are booting virtual machine in several minutes, but they don't know how to manage to make it fast. But virtual machine can be really fast. The other problem on performances is, what is really your performances problem? Is your bound the RAM? RAM is never the bound. RAM is cheap. You have no problem of RAM. Is the bound the CPU? CPU burning people? No, because CPU, you know, we manage thousands of applications. Problem of CPU are really, really rare. The problem is not on the CPU. The problem of performance is on the input-output, on the storage and the network. And the problem with input-output is you can manage it with a virtual machine because you can have direct access to the hardware, but you cannot manage it inside the proxying system, inside a container. This is why there is so much trouble inside the stateful container people. And you need to choose your fight on this. There is many Linux low-level magic. Everybody say to me, you will use Alpine Linux inside Docker because Alpine Linux are light. Because, you know, we hold using Docker, it's 2 more megabytes of data. Cool. Why IP Linux is so light? What? Nobody? IP Linux is so light because they have kicked the glibc and rewrite a very weird binary compatible thing able to replace the glibc. Basically, at the first, there was on microclibc, and now there is on a new project called Muzzle. And basically, if you are looking on the Alpine Linux project, all the important package are maintained by only one guy, which is the main maintainer of the Muzzle project. Cool. And people are saying to me, we're using Docker for have extensional use from the developer laptop to the continuous integration to production using something nobody knows about, which is the glibc. I remember the glibc is managing the network, the access to the hard drive, all the things like that. And this is the kind of low Linux dark magic. If you want to use this kind of stuff, just trying to understand this kind of stuff. The other part is the dependency model. Just explaining. If you have a code, you have your code, and the dependencies is managed by the build system. Then you have the libs of the code, and the build system maintain it. You need to be stick inside, and then developers are responsible for this part and ops for this part, okay? If you're using a container or a virtual machine as the way of process building, the developer becomes responsible of all of this. There is no more flexibility inside it. And the problem with the flexibility is developers don't upgrade library in their code. Why they will upgrade OpenSSH issue when it happens? Do you really need, when you are writing a Java Spring Boot application, to have an exact dependency control on the low-level Linux binary system? I'm not sure with that. I'm not sure with the dependency monolith, you know. Like, I prefer to have many levels of working. And this is the way I want to speak with you, is French people have misunderstanding DevOps. DevOps is not developer making the job of ops people. DevOps is the way of communication of the two. And in many companies, the problem is developers just want to make the job of ops people instead of job people, because the ops people have always said no. It's only because the ops people are badly managed in a weird organization and sometimes not competent enough. But the problem is not the ops people, the problem is the organization. And you really need to focus on that, because it's not the good sense of the history, you know. The sense of the history is you have one competencies, not the competencies of many people. So please remember about virtualization and containers. Containers are not like VM. It's simply not true. And the container isolation is not trustable for third-party code. Basically, container security is about to making mutualized PHP. Without PHP, but all the binary we want. So I don't say don't use Docker. I say use it wisely. And if you want to be a Docker expert, like a lot of people want to be these days, just read the release note of the kernel and start learning how it's working deep inside. Okay, thank you a lot for listening. I hope you will try Clever Cloud. And if there is some question, I can take it. Thank you very much.